Hi, I'm Mike Gordon,
And I'm Brad Jackson.
and this is going to be our demo project for MAE 535, Design of Electromechanical Systems. What we're going to do today is talk about the design and setup for a basic railgun, or in this case, more accurately, a linear homopolar motor. What we've got here for our setup, we've got two rails, which in this case we've got two pieces of aluminum bar stock. We've got our armature, so a little metal piece of coat hanger and a couple magnets attached on the end. And we've got our voltage source, a 9-volt battery. Basically what we're going to do is we're going to create an electric field which is going to run a current down one rail, across the armature, and back down the other rail, which induces a magnetic field, and that's going to create a forward motion for our little armature or our bullet.
So the magnetic field that's being generated can be defined by the Biot-Savart law, which relates the current to the direction of travel. So you can see when you flip the switch here, the bullet goes forward. But if you switch the direction of the current flow by swapping the leads on the battery, then it'll go in the other direction. You can accomplish the same thing by taking the magnets on the end and flipping them around so the poles are in the opposite direction, which will also cause the direction of travel to switch.
So this motion is actually caused by a Lorentz force, which basically describes a charged particle which is moving through an electric and a magnetic field. In this case, we've got our electric field, which is created by the current loop from the battery. We've got our magnetic field, which is induced by that electric field, which actually forms around each of the rails, and then that net magnetic field along with the current from the battery is what's going to propel that forward with Lorentz force.
The other thing about this is you can also describe the magnetic field through Ampere's law, which is derived from the Biot-Savart law. But Ampere's law relates the magnetic field intensity H to the current density J. So what we did here is we prepared a second model using aluminum foil instead of aluminum bar stock. The difference in this is the lower cross-sectional area in the aluminum foil is going to give us a higher current density. So when we hook this up, you'll see is when we flip the switch, if our magnets don't get stuck.
Yep.
There we go. Is that the projectile moves a lot faster. So there's obvious ways to improve on this design to get it up to where railguns currently are in terms of technology. And the first notable drawback we have is our lack of a decent voltage or current source. Typical designs use large banks of capacitors to generate a much higher current, much higher voltage, and in turn impose or generate a higher magnetic field, causing a faster projectile motion.
So there's also a lot of drawbacks, obviously, to these railgun designs. Like Brad was saying, you need a huge capacitor bank to produce enough current to actually shoot a bullet or our armature, and running that kind of current through these rails here actually produces a huge amount of heat, which you can have you can cause a lot of damage to the rails after firing even one time. With larger railgun designs like they use in the Navy, you actually need to create some kind of initial velocity, otherwise the bullet immediately spot welds to the rail. And in our case here, one other thing to note is that since we've got such a small bullet here and such a small current source, we actually have to mimic the Lorentz force that would typically push these push these rails apart, which again you see with a larger design, you have a huge Lorentz force which actually again pushes the rails apart. So we mimic that in this design with two magnets here and their reverse polarity.
So that's our project. Hope you enjoyed it.